Welcome everyone to this presentation on traceability, a very important topic. There's several different sources concerning traceability you can go to. The INCOSE System Engineering Handbook version 5, section 323 has greatly expanded coverage of traceability compared to what was in version 4. And then members of the requirement working group co-authored a paper, Traceability: A Vision for Now and Tomorrow, with the Configuration Management Working Group that was presented at IS 2024 by Adriana de Souza. This presentation is going to focus on the coverage of traceability that's in the Needs and Requirements Manual. We released version 1 in January 2022, updated in May of 2022 to shorten the title, add subtitle line with other products that were being developed. It also aligns with the INCOSE SE Handbook version 5 as well as the CBOC. And it's been updated to version 2, which has been published by Wiley. You can go to Wiley to get a hard copy, and we're working on getting a PDF put in the INCOSE store for download as well. So in Chapter 3 of the Needs and Requirements Manual, we talk about moving from a document-centric to a data-centric practice of system engineering, which we feel is the real intent of MBSE. As you can see in this chart, there's a whole lot of artifacts and activities associated with developing a product. As artifacts is any data and information that's created as part of system engineering. When we're doing a elicitation, we're capturing the stakeholder needs and requirements. Those are artifacts. When we define driver's constraints, each of those are artifacts. When we do risk assessment and we define risks that need to be mitigated, those are artifacts. Our lifecycle concepts that we define, that information that communicates that's an artifact. The needs requirements are artifacts. All of our design decisions and design descriptions are artifacts. The design output specifications are artifacts. The artifact is any combination of data information that's generated as part of developing the product across the lifecycle. The lines show the relationships, and traceability is critical to documenting these relationships. The importance of traceability has been amplified for highly regulated products and industries. The standards and regulations call out the need for traceability. ARP 45754A, Guidelines for Developing Civil Aircraft Systems, requires requirements dealing with safety to be uniquely identified and traceable to ensure visibility of the safety requirements at the software and electronic hardware design level. ISO 26262, road vehicles functional safety, requires safety requirements shall be traceable with a reference being made to each source of the safety requirement at the upper hierarchical level, each derived safety requirement at the next lower level to its realization and design, and traceability through the verification specification in accordance with the section. USC Title 21, Part 820, Quality Management System for Medical Devices, requires the developing organizations to develop and maintain a device history file that shall contain or reference records necessary to demonstrate that the design was developed in accordance with the approved design plan and requirements of this part. Again, traceability is very crucial to that. And then more recently, it's being updated to include the provisions of ISO 13485. And Section 3.2 requires organizations to document methods to ensure traceability of the design and development outputs of design development inputs. Failure to show traceability to these agencies can result in a product not being approved. So it's extremely important in that world. If I'm the FDA and you've identified a risk and you decided to mitigate that as part of your design, then I would expect to have the risk, the needs associated with the capabilities to address that, the design input requirements, and the implementing design artifacts. I expect those to all be linked together, as well as linked to the verification and validation artifacts, so you can show to the FDA objective evidence that you have satisfactorily addressed that risk. So what exactly is traceability when you talk about it? All the artifacts that showed in the previous chart, the individual sets of lifecycle concept needs and requirements, which are referred to as CNRs, design specifications, system validation artifacts, system verification artifacts, and other artifacts that we generate across the lifecycle. Again, they don't exist in isolation. Rather, they represent a multi-level spider web, or recently I've heard the term tapestry, of relationships that represent a data and information model of the integrated system. And these relationships are documented via traceability connections, links that allow these relationships to be traced between the entities that are linked both vertically across levels and horizontally across the lifecycle. So this is the fundamental concept of traceability. So from a definition standpoint, traceability is the ability to establish an association or relationship between two or more entities and to track entities from their origin to the activities and deliverables that satisfy them, as well as assess the effects on artifacts across the lifecycle when change occurs. And I'll talk about it a little bit later, but a lot of people, especially in the older days and a lot of the classes I taught, I remember traceability was associated with parent-child relationships or requirements. And that's when we really talked about traceability. You notice this is a much broader definition, where we're talking about any of the artifacts, relationships, and traceability being able to document those relationships. And traceability can be bidirectional, unidirectional, horizontal, or vertical. Bidirectional traceability is the ability to establish a two-way link between entities such that each has knowledge of each other. The benefit of having bidirectional traceability is that we can move forward, backward, up and down the digital threads or the tapestry that result from establishing the bidirectional traceability. And although the relationship is created in both directions, it's not really the same relationship. For example, one direction should be indicated as trace from or trace to. Similarly, satisfies or satisfied by are two different directions within a bidirectional satisfied relationship. Unidirectional traceability is the ability to establish a one-way trace from one entity to another where the source entity has no knowledge of the receiving entity. So for example, we have a trace from entity A, but entity A has no knowledge that entity B has traced to it. GPS satellites, any broadcasting system is like that. Then we have horizontal traceability, and that involves the forward-backward traceability between entities across the lifecycle. So horizontal traceability links data and information artifacts generated in one lifecycle process activity to the data information artifacts generated in other lifecycle process activities, resulting in a digital thread connecting these data information artifacts across the lifecycle. So here we have stakeholder expectations linked to lifecycle concepts, to needs, requirements, to the design, the system of interest, and also to the verification validation artifacts. We also may have done a risk assessment, come up with a risk mitigation plan, define needs that reflect capabilities to mitigate that risk, and then the same kind of traceability. One of the flagship diagrams that we have in the requirement working group is this diagram, and it shows that we start with stakeholder real-world expectations, which are transformed into an integrated set of needs, are transformed into design input requirements, transformed into design output specifications, transformed into the realized system element, then are operated, maintained, and disposed of. All these transformations are generating different artifacts, and they need to be linked together across the life cycle. And then when we talk of verification validation, we're always verifying, validating something against something. And so we need to have that traceability established also. Needs, requirements, verification, validation of the common threads that tie all lifecycle activities and artifacts together. We talk about vertical traceability. It's most often referred to in context of levels of an organization or architectural levels. Each level has its own set of lifecycle concept needs and requirements defined for the entity. Organizational business level requirements drive the development of operational lifecycle concept needs and requirements. As the operational lifecycle concept needs and requirements are defined, traceability is established with their high-level business requirements that they're addressing, and then this repeats for each level. So all the red lines, you can see we have traceability from one level back up to the previous level to show compliance. And then from a system development standpoint, we think about this hierarchical view of a system. So each part of the system of architecture is represented by a family of system engineering artifacts. And artifacts at one level drive the definition of artifacts at the next lower level, like was shown in the previous chart. And the artifacts at the lower level must trace the artifacts generated at the next higher level. So we have level 5 artifacts that trace the level 4 artifacts, that trace the level 3 artifacts, trace the level 2 artifacts, and so on. But a major issue with this view is each of the parts is often managed in a silo, developed in the silo, and this view doesn't show the relationships that exist between the different parts of the architecture. So we have all these different relationships, and that's what really traceability is about, is establishing these relationships. Taking a more holistic view, we see that all the parts are interconnected, have relationships, and we know the behavior of a system is a function of the interactions of its parts and interactions of the system with its operational environment. System engineering can be viewed as a system made up of various artifacts and the relationships between those artifacts. Traceability enables identification and management of relationships between these various artifacts. So again, we talked about horizontal and vertical relationships in the previous chart. Before I talked about more of the vertical relationships, but you notice at each level, there's stakeholder real-world expectations, there's lifecycle concepts, needs, and requirements. All of these are linked together horizontal, and then they flow down and drive the next level of activities. And those activities then have stakeholder real-world expectations at that level, lifecycle concepts. So we have horizontal traceability at each of these levels, in addition to the vertical traceability to establish those relationships. So again, the types of relationships, we talk about the design input requirements, linking to the implementing design artifacts, the design output specifications. We have requirements traced to the verification artifacts. We have needs traced to the validation artifacts. So a lot of different relationships that we're capturing with traceability. And then a real key relationship is the flow down of a requirement at one level to a lower level part of the architecture, which we refer to as allocation. Notice when we do this and establish a traceability relationship that when we're doing allocation, we're linking a requirement to a part of the architecture. And we're not linking a requirement to a requirement at this point in time in allocation. Once we've allocated requirements to a part of the architecture, then child requirements then will be developed and then they will trace back to their allocated parent. And so the trace is a requirement to a requirement, whereas allocation is a link from a higher level requirement to part of the architecture that has a role in meeting that requirement. The common thing I talked about before is managing the parent-child relationships. In the past, that's been a major part of what traceability is about, like I said, and it still is important to understand what those relationships are. So we need to have allocated parent requirements and then the child tracing back to their parent. And it's common, and especially in the document-centric world, that we have trace matrices to view these relationships. So we have a need traced to a system requirement, traced to a subsystem requirement, traced to multiple subsystem element requirements. And of course, there's additional subsystem requirements would be shown also below this. You can see in this example, we have requirement number and we have the text. And so we can look at this and see the appropriateness of the allocation. Another point though, consider I have 500 requirements. Doing it in this form can be problematic. So we need other ways to be able to document this. And in SysML models, we have traceability matrices that we can develop. On the right is a simple one with just a few needs and requirements that are linked to each other. On the left is much more complex. We have 40-some customer needs, and then we have requirements that implement those needs. This chart's not complete. There's a lot more rows that are not shown. But you can look at each of the marks and you can see the relationships. So I can look across horizontally to see requirements that address certain needs. I can go down a column and for a given need and see which requirements address that particular need. A lot better way of being able to manage this. Also, when we talk about types of relationships, one is requirement to a source. In the past, we always talk about requirement to a parent requirement, but there's other sources besides the parent requirement. In our products, we talk about that the design input requirements are transformed from integrated set of needs. So those design input requirements would be traceable to that integrated set of needs. We may have been provided a set of customer requirements and associated standard regulations, so those could be sources as well. While the focus in the past was parent-child, we have to recognize that there are other sources that we can point to, and the parent is just one of those sources. And also, when we talk about the integrated set of needs, they have a source, so they must be traced to where they came from as well. Another type of relationship is interface requirements trace to an interface definition. So in this case, we have a subsystem B, a subsystem C that are interacting across the interface boundary. And so each requirement you want to trace to a common definition on how they're going to interact. Establishing a trace from the requirement to those definitions is critical. When you read in the needs and requirements manual, when we talk about interfaces, I talk about doing an interface audit. And if these trace links are established within the tool, it's easy to do that audit to make sure we don't have any issues. You also see in here that subsystem B and C child requirements are in response to a system A parent requirement. So we have the trace to parent, but also because these interface requirements show a relationship between the subsystems, we also have a trace to peer. That's one of the key types of relationships is the peer-to-peer relationship. And this is often requirements at the same level, either within the same set of requirements or requirements contained in different subsystem or system element sets of requirements. The relationship could be general or grouped by topic, such as connecting requirements of a particular theme, connecting interface requirements, requirements sharing a common budgeted quantity, and connecting performance requirements that relate to a common function. A lot of times there's a dependency that we have to manage, and this shows a relationship of one requirement to one or more requirements that to be completed, they have to either be completed together. You can't just do one or other, you have to do them both in order to satisfy the parent. There can be other requirements that represent specific conditions or a relationship of another requirement such that a change in one can result in the need to change the other. So this is really important in change control to establish those dependencies. So if there is a change, you have to assess the impact of the other peer requirements that are linked to it. And the other requirement is not necessarily in the set that the one requirement's in. The dependency could be a different system, subsystem, or system relevant requirement. When we talk about allocation and budgeting, this is a classic dependency. In this example, I have a power requirement overall for the system. That power's use requirement is allocated to subsystem B, C, and D. They're each the budgeted portion of the power that they're able to use. This results in an equation. So subsystem A total value equals the sum of the subsystem B, C, and D. It's the budgeted power. And we always have to keep this equation in balance. So these budgets need to be managed and controlled at the integrated system level. The critical concept associated with requirements and budgeting is that the budgeted quantities result in the dependencies. So budgets must be carefully controlled as they tend to change as the design matures. In the early stages, they can be very dynamic, and so we need a way to manage these. One subsystem may need more power than was allocated, another less, and so we need to manage that. And that's a key part of integration, is to manage those budgets. So both the trace to the parent and trace to the peers that have the dependency is critical to being able to manage and control those budgeted values. It could get complicated. We have dependencies at lower levels. So I may have the budgeted system A requirement. I may have the budgeted subsystem B, C, and D requirements. They each have children requirements. And here we have subsystem B requirement that has a dependency with subsystem D low-level requirement. So I have these equations at multiple levels, and I have a dependency. So this may not be obvious. That's one of the key things about the use of modeling is to help identify these kind of dependencies across multiple levels of the integrated system model. And then we want to capture these dependencies through traceability. Another type of relationship, typically a project has multiple tools, and you can have similar data in different tools. We may have requirements in requirement management tool. the same requirement may be also being shown as an entity within a language-based modeling tool. And so we need a way to link those. And there's a lot of companies now coming up with either way to do this directly, or there's some type of a data integration tool that allows linking this information together. By linking this together, we can not only be able to share data, but also help ensure consistency and establish an authoritative source of truth. So another relationship that traceability helps us manage. And then I talked about models. Within our different models, a lot of the benefits of using traceability can enhance with the models. When using SysML tools, there are additional ways requirements can show relationships to other requirements or other elements within the model. For example, for SysML applications, requirement diagrams are used to display textual requirements, relationships, and also those traceability and allocation matrices you can develop within the models. Most requirement relationships in SysML are based on UML dependencies. So the arrow points from the dependent model element, the client, to the independent model element, the supplier. And in SysML, the arrow's direction is opposite to that typically used in requirement flows, where the higher level requirement points to a lower level requirement. We have different types of relationships and dependencies. We have containment, trace, derivation, refinement, satisfaction, and the verified relationship. So these are all set up that we can establish within our model as part of our traceability management. We can combine allocation and traceability to better manage our requirements. And sadly, a lot of organizations don't do this, which can result in defects within our sets of requirements. Combining the concepts allocation and traceability provides a powerful method to manage our design input requirements, especially across levels and across subsystem system elements. Unfortunately, the concept of allocation is not well understood as traceability is, and there's several common misconceptions and bad practices. Some feel they can use traceability matrices to assess allocation. The thought process is that if a parent has a child requirement defined for a subsystem system element, it's safe to assume that the parent must have been allocated to that subsystem, and this is often a bad assumption. Missing information in the traceability matrix. Another issue is that when traceability matrices are developed, rather than include the requirement text like I showed in that one example, or at least a summary title or something, in the matrix, all the requirement numbers are used. And in the SysML, only that little arrow was used. So when you're looking at those, how do you assess the validity and correctness of the allocation and traces? It's really hard to do this assessment without actually knowing what the text of the entities are that are being linked together. I find at a lot of conferences, not all tool vendors understand the real meaning of allocation and thus do not always implement the concept correctly within their tools. So one thing I do is I ask tool vendors, can you generate a report that lists all child requirements that trace to a parent requirement that was not allocated to the subsystem or system element in which the child requirements exist? And I get a deer in the headlight kind of response from the tool vendor because they have no idea what I'm talking about, which is kind of sad. In combining allocation and traceability, we can check for various different kinds of defects. Parent requirements that don't have any child requirements. They were allocated, but there was no child requirements developed to implement the parents. We have needs with no implementing design input requirements. We have orphan needs that don't trace to a source. We have orphan requirements that don't trace to a need, parent, or source. Need source and requirements with incorrect or missing implementing children. Child requirements with an incorrect parent or source. Sets of child requirements that are not necessary or sufficient to implement the parent requirement, need, or source. Addressing these issues is hard, can take considerable amount of time and effort. There's some things that we could get out of our tools, or we could form a query that would look at the different attributes and could answer some of these, like parents with no child or needs with no implementing, orphans that don't trace. These can all be done with a report from your tool. But there are some things like incorrect or missing, incorrect parents, the sets are not sufficient. Those are all thinking, intelligent kind of things that the human has to do. When we have large sets of requirements, it's important that we do these assessments, but because of the time, unfortunately, like I said, a lot of people don't do that. I worked for a project once and they wanted me to do an assessment of the allocation traceability from level 1 down to level 5. The only thing I had was the allocation trace matrices that were included as appendix for each document at each level. And I tried to combine all those, and I had like 1,000 rows and 1,000 columns, it seemed like. But there are so many disconnects. When you get that large number, it's very hard to manage that. So that's one big reason for moving to a data-centric practice where we're managing all those within a tool. I mentioned the ability to generate reports from the tool. So rather than me assessing 1,000 requirements to see if they all have children, I should be able to write a query that should just list all the requirements that don't have any children. So I don't have to do that manually. The report from the tool allows me to do that. So one of the big things about traceability is it really helps us to manage change. This is a traceability relationship metal model. It shows all the different artifacts. It shows those all linked together through traceability. You can see that if I change any one of these, I can immediately go back to everything connected to that to see if any of those entities are impacted by the change. And managing requirements in a document without having this traceability across the lifecycle, it's extremely hard to do that change impact assessment. So it's very important that we define this model at the beginning of our project and then implement that within our tool set. And this bidirectional traceability is critical to document the relationships, assess change, and show compliance. I'm developing a data information model of my system and of my artifacts. And so the data and the relationships between the data are part of that model. Rather than baselining a specific document, I would baseline the data and information model, which would include, like I say, the data and the relationships. In Chapter 14 of the Easy Requirements Manual, we talked about configuration management and the baselining of the data information. When we're doing this, the traceability are very important, especially when it comes to the change control and doing change impact assessment. Also, what I was showing before about consistency with data that's maintained in different tools. From a change management perspective, traceability helps us do that. If there's a requirement in a requirement management tool and a corresponding requirement in language management tool, if you change that requirement in either place, I should be able to have that knowledge in the other tool and make sure that that same change has been implemented. That's very critical in our systems. And so in closing, some guidelines for recording, managing traceability. There's a range of tools available for establishing and managing traceability. Unless you have a small set of requirements, it's highly recommended the project team use the requirement management tool or other application. You can see if I try to manage all this in Excel or just in tables, it can really get out of hand and I can really have it broken. The tools to use to manage traceability records should be identified at the beginning of the project, and traceability can quickly become complex. Switching tools mid-project could present major challenges. So you got to establish this at the beginning of the project. When I mentioned that I taught requirement classes, and in the old days, the only real relationship was parent-child relationships and traceability. There was legacy tools that are on the market still today that developed to be able to manage that traceability, but they did the traceability in a silo. Today, the modern requirement management tools allow you to establish traceability across the lifecycle. It's not just requirements in a silo, it's all those artifacts across the lifecycle that you manage within the tool, and the tool enables you to document those relationships through traceability. So pick a tool that allows you to do that across the lifecycle, not just in a silo. And when models are used as an analysis tool to identify needs and design input requirements, the tools in the project toolset need to enable traceability between requirements of the models from which they were derived, even if the data are defined and maintained within different software applications. This is key to being able to maintain consistency and correctness of the needs and requirements, no matter which tool is used. And this also enables the ability to change a needed requirement in one tool and have that change reflected in another tool. So there is that authoritative source of truth. Design input requirements that are transformed to an integrated set of needs. We need to establish trace between that requirement's related need when the requirements are defined and recorded. And this is true for anything. Whenever we enter information within our tools, we don't want to put off establishing the traceability to later. We need to establish that traceability as the data is entered. Child requirements create a response. We need to establish that trace as well. So that's where I go back to this traceability relationship meta model. That needs to be defined within your tool. A lot of the tools allow you to establish rules to help enforce this model. So with the rules, then if you fail to follow the rules, establish traceability, then those tools will flag that error, bring it to your attention so you can fix that problem and maintain the traceability across the lifecycle. Other guidelines, it's important that all requirements must trace to a need source or parent. Requirements that do not have this trace are referred to orphan requirements. Even a requirement does not trace to an allocated parent, there should be some kind of source of need to which it's transformed. Again, no orphans. I've seen some tool vendors actually teach in the class that orphan requirements are okay. They even introduce the concept of a self-derived requirement. Just the engineers know they need it, so they just define it anyway. That's really a bad practice. When you're moving down levels of abstraction from system level to subsystem to system elements, when you allocate a parent requirement or when you define the needs and you transform the needs to design input requirements, you do requirements analysis to see what the lower level needs to do to meet the parent or what a set of design input requirements needs to do to realize a need. As a result of that analysis are going to be the child requirements or design input requirements. This can be done through derivation, elaboration, or decomposition. So there's three different things that can take place that result in either the child requirements or in the design input requirements to meet the intent of the need from which it's transformed from. All requirements, like I said, must trace to a source or a need or a parent requirement. There should be no orphans. It's best practice to define system verification attributes when a requirement is defined, as well as system validation attributes when needs are defined. When you do this, you should be establishing traceability to the system verification and validation attributes when the needed requirements initially defined and recorded within your tool. It could be that you have another tool that were used to manage verification and validation activities. So in that case, this traceability may be a link to that other tool. It's also best practice to trace requirements to the test cases within a verification plan or a procedure that executes the system verification activity. And when child requirement traces multiple parents, needs or sources, each trace must be assessed for its validity whenever that happens. And the trace to all requirements to a parent, source, and need should be verified independently, if possible, to ensure that requirements trace is correct during requirement verification. When you go to the Needs and Requirements Manual, when we have defined an integrated set of needs, then we verify and validate those needs, the quality of the needs, and part of that is ensuring all the needs trace to a source. Well, after we defined our set of design input requirements, we do requirements verification validation to make sure the quality of the requirements and the intended requirements is proper. And so again, we're going to assess traceability as part of these needs and requirements verification and validation activities.
Thank you, Lou, again for this informative presentation.